the side B is given and it equals to this altitude, then you have the one solution, which is the right-angled triangle. That is, one solution is possible, and it is the solution of the right-angled triangle. So if B is equal to H, one triangle is possible, which is the right-angled triangle. And it can be solved. So you have only one set of solutions for this right-angled triangle. B is equal to 11.472. You can determine what the angle A is, which is 55 degrees. You would simply have to find this amount along the base, and the triangle would be solved. So under those conditions, we have one solution possible. There is another case where one solution is possible, and it is if B is greater than C. In other words, in this case, if B is greater than 20, this arm acts as though it's on a hinge. So if the length of B is greater than 20, like 21, for example, there is again only one solution possible, and you have enough information to find out what that is by using the sine laws. So there are two situations where one solution may occur. One, if B is exactly equal to the altitude from A to BC, or when B is larger than this length given. I will complete the solution for the more difficult case. Finally, if B is greater than the altitude, or this perpendicular, greater than C sine B, but less than C, 20. Then there will be two solutions. I'm going to leave this part of the diagram on the board and continue with the solution given these components. Angle B is equal to 35 degrees. C is equal to 20, and B is equal to 15 units. Solve the triangle. First of all, make the following observation. H, the perpendicular, is equal to 20 sine 35 degrees, and that's approximately 11. We saw that. And B is greater than 11 given. We know we have at least one solution, but the fact that B is also less than C, in other words, B is less than 20, we know there are two solutions. We will draw the diagram a little more carefully. And in fact, we will draw two diagrams. What happens here is when B is larger than the perpendicular, then here is one solution possible. That makes b equal to 15. B is equal to 35 degrees. C is equal to 20. Here we have the vertex A, and we need to know what capital A, capital C, and small a equals. Now the other triangle is, if you assume again that B is hinged at A, that this arm can swing around and cut the base at another point here, resulting in an isosceles triangle, of course. But the two triangles that are now under study is one that looks like the one I have just drawn, and the other one looks like this. This triangle has exactly the same given components as this triangle does. This is still 20, this is still 35 degrees, and B is 15. And so, in solving this triangle, you must solve those two triangles. Let us begin. We have two sides and this angle not contained. Let's refer to this as diagram 1. There are two sides and two angles in the sine law. So using the sine law and those components, we'll have to use B and C, and therefore write B over sine B equals C over sine C. B is 15. Sine 35 over sine 35 degrees is equal to 20 over the sine of C, which is not known. Make sine C the subject of this equation, and we have that the sine of C is equal to 20 over 15 multiplied by the sine of 35 degrees. Working this out on a calculator, sine 35 multiplied by 20 and divided by 15 is equal to 0.7647. Approximately. So the angle C is the arc sine of this amount. And that is equal to 49.886 degrees approximately. So we have this angle now equal to 49.886 degrees. If you examine the triangle, we see that angle A can be determined simply by subtracting from 180. So 180 subtracting the sum of 49.886 and 35 amounts to 95.11 degrees approximately. We have only one component left to solve for in this first triangle, and that is to solve for small a. Now small a can be solved by using a over the sine of a equals any of the other two ratios that are available. Let's take 15 over the sine of 35, which is b over sine b. It's safer to use components that are given rather than components which you have solved and are approximate. So then, a over the sine of 95.11 degrees is equal to b, which is 15, over sine 35, and now we simply continue and solve for a. 90, 35.11 taking its sign is equal to 0.996 approximately. Multiply it by 15 and divide by the sine of 35. And the answer is approximately equal to 26.048. And that triangle is now solved for. Here are the components: A, C, and of course I found the third one. I will now do part 2 of this solution, and that'll be about the components of this smaller triangle. We'll take all of this off and repeat. Some of the work that we have already done can be used again. For example, if we know that this exterior angle here, since this is isosceles from this diagram, this is 49.886 degrees, then this in here is 49.886 degrees. And that's the exterior angle to this interior angle C. These two are equal in length. So in this isosceles triangle, looking at the first diagram, if this is 49.886, then this is 49.886, and so is this 49.886. Well, that's the exterior angle to this interior one. And since this is a straight angle equal to 180 degrees, then we can determine that angle right there at C is equal to 180 minus 49.886 degrees. And so it equals 411 decimal point 0 and then 13. So this angle C is now 130.114 degrees, and we don't want to look at the rest of these lines which were used in that analysis. We can now find what angle A is by the interior sum of the angles of a triangle property. It is 180 degrees minus the sum of the other two, which is 35 degrees plus 130.114 degrees. That is 180 minus 165.114 degrees, and that finally equals 6.884.1. 14.886 degrees. I better enclose these in different colors so I don't lose track. So what remains to solve for? We have the three angles, 35 degrees given, and now these two. We have the two sides, and so what remains is simply to find what A is. Small a over sine A equals, it doesn't make any difference what other ratio we use, I'll use B over sine B. A is not known, sine of angle 14.886 degrees is required, and that's equal to the length B, which is 15, over the sine of 35 degrees. Working this all down using your calculator, and that equals 6.718 approximately. And there we have all of the components for that triangle. Now, next is the cosine law. This law will solve the triangle given two sides and the contained angle. The contained angle is the angle formed by the arms of the given sides. The formula is a squared equals b squared plus c squared minus 2bc times the cosine of the angle A. Notice that the first three terms here, a squared equals b squared plus c squared, will remind you of the Pythagorean theorem formula, where if A is the hypotenuse and B and C are the other two sides, then looking only at that part of the equation, a squared equals b squared plus c squared. Then the rest of it, minus 2bc cos A, is needed in order to deal with triangles that are not right-angled. The term negative 2bc cos A, all of that portion, may be positive or negative depending on the size of angle A. If A is an acute angle, the cos of A is a positive quantity, since the angle is in the first quadrant of the Cartesian coordinate graph. Consequently, all of this will be negative. But if A is a second quadrant angle that is larger than 90 and less than 180 degrees, as you would find in an obtuse angled triangle condition, the sine of the cos of the obtuse angle would be a negative quantity. And this negative quantity multiplied through here by negative 2 will make the entire amount a positive term. So this entire amount will be positive or negative depending on the size of A. If A is acute, then cos A is positive, and the entire expression, negative 2bc cos A, is negative. But on the other hand, if A is obtuse, as in an obtuse angled triangle, cos A is negative, and negative times a negative makes this amount positive. You would use this formula when the given components of the triangle are side B, side C, and the angle contained, which is A. This allows you then to solve for the third side that's not given, A. You must memorize that formula. And think of it in this fashion to help you memorize it. Think of the first three terms as part of the Pythagorean theorem. The other term is constructed this way. It's negative 2 BC cos capital A. And here you have small a, and so there you will have capital A. Now, of course, if it's B or C that you have to find, because the other two sides are the ones that are given, then by association you should be able to write out the other two formulas. One for B squared and the other one for C squared. Now, once you memorize one of the formulas, like the one I have in the red box, you simply have to write the other two down by association. If A squared equals B squared plus C squared, it stands to reason that B squared must equal A squared plus C squared. The rest of the pattern follows, minus 2AC cos capital B. Similarly then, C squared is equal to A squared plus B squared minus 2AB cos capital C. So if you remember the one in the square box up there, you should have no trouble remembering the other two by making comparisons term by term. The cosine law. Given two sides, B and C, and the contained angle A, prove A squared equals B squared plus C squared minus 2BC cos A. Acute angled and obtuse angled. A, B, C, A, B, C. Drop a perpendicular from C to AB or BA produced. And call it H. If we allow this portion of the side C to equal X, the remaining part of the length AB will be equal to C minus X. This is side B and this is side A. We're assuming that B and C are the given sides and the contained angle is also given. This side is A This side is B, and this side is C. Let's call the amount produced along BA as x, the length x. In this triangle, we have that b squared is equal to x squared plus h squared. Similarly, in this right angle triangle here, by the Pythagorean theorem, a squared is equal to h squared plus c minus x quantity squared. Simplifying, a squared is h squared plus c squared minus 2cx plus x squared. Now examine this line, the last one, and notice that I have h squared and x squared on the right-hand side of the equal sign. That is also found in this first statement, x squared plus h squared. These two terms can be replaced by b squared, and I can write, therefore, that a squared is equal to b squared plus c squared minus 2cx. Looking at the small right-angle triangle, x over b is the cosine of angle A, or x is equal to b cos A. We replace the x, therefore, by that amount. In other words, a squared is equal to b squared plus c squared minus 2c b cos A. And 2cb cos A is the same as 2bc cos A. Proof is completed for the acute angle triangle. On the other hand, we have in this triangle, in the obtuse angle triangle, the fact that b squared is equal to x squared plus h squared by the Pythagorean theorem. Similarly, a squared in the large right angle triangle, a squared is equal to h squared plus x plus c quantity squared. Simplifying, a squared is equal to h squared plus x squared plus 2xc plus c squared. We have